Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the purple shaded region? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Three identical tangent circles surround the small purple curvilinear gap DEF. Each circle has area pi, and the target is only the purple gap, not the straight triangle around it. Our strategy is to join the three centers, A, B, and C, into a triangle. Then subtract the three rounded corners the circles carve out of it. So the purple area will equal that triangle minus three circular sectors. And we will build each piece in turn. Start with the radius, since every later step depends on it. The area of any circle is pi times the radius squared, and we are told each of these circles has area pi. Set the area formula equal to the given value by writing pi times r squared equals pi. This is the equation that pins down the radius. Divide both sides by pi, which is valid because pi is not 0. That cancels the pi and leaves r squared equal to 1. Take the positive square root, since a radius must be positive. Each circle has radius 1, a clean value we will use for both the side lengths and the sector areas. Next, we need the triangle's side length. When two circles touch on the outside, the distance between their centers equals the sum of the two radii, because the tangent point sits right on the line joining the centers. Both radii equal 1, so each pair of centers is 1 plus 1, that is 2, apart. Every side of the center triangle, therefore, has length 2. Now draw the construction. Connect the three centers with the segments segment AB, segment BC, and segment CA to form triangle ABC. These joined center lines are the frame we measure the region against. Aha! Every pair of tangent unit circles has centers 2 units apart. The same 2 radius distance holds for segment AB, segment BC, and segment CA. So pairwise tangency makes center triangle ABC equilateral. Each tangent point lies 1 radius from both neighboring centers, and each side is too long, so D, E, and F are exactly the midpoints of the sides. This tells us where the sector radii will land. The area of an equilateral triangle is root 3 over 4 times the side squared. We will feed our side of 2 into this formula. Substitute the side of 2 into the formula and square it, giving 4. Root 3 over 4 times 4 is coming next. The 4 in the numerator cancels the 4 in the denominator, leaving just root 3. So triangle ABC has area root 3, our first main piece. Every angle of an equilateral triangle is 60 degrees, and the three of them add to 180. Each corner sits at a circle's center, so a 60-degree wedge of that circle lies inside the triangle. Draw the 2 radii from center A out to the tangent points E and D. These radii, each of length 1, bound the little corner wedge of circle A that pokes into the triangle. That wedge spans 60 degrees out of a full 360, so it is 1/6 of the whole circle. A sector's area is that same fraction of the circle's area. 1/6 of pi times 1 squared is pi over 6. So the corner sector, i.e. D, has area pi over 6. Now draw the radii from center B to the tangent points E and F, forming the wedge B, EEF. By the same 60-degree reasoning, its area is also pi over 6. Finally, draw the radii from center C to the tangent points D and F. giving the wedge C df again pi over 6. That completes all three corner sectors. Aha. The three central angles are 60 degrees each, so together they span 180 degrees. With unit radii, such as segment AE, the three 60-degree sectors combine to one half circle, even though they sit at three different centers. Subtract the three blue sectors from the equilateral center triangle. What remains is exactly the purple curvilinear gap DEF, with area root 3 minus pi over 2. Let us sanity check the size. Root 3 is about 1.732. Pi over 2 is about 1.571, a little smaller than root 3, so the difference will come out positive. Subtracting gives about 0.16. A small positive number is exactly right for that thin patch squeezed in the middle. So the purple gap DEF has area square root of 3 minus pi over 2 square units. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.